So we've got now how organisms are distributed. We've got how many organisms can survive in 1 unit volume. Now we're going to talk about their various life history traits, how often they can reproduce, how many offspring they produce, and so on. Populations dynamics, so how a population increases or decreases in size is going to be influenced by its life history traits and by its population density. For instance, if we're talking about deer quality versus deer production, how many deers are present, population size, what you're going to see is as you have more deer present in the winter, think about deer in winter, the more deer there are in winter, the lower quality of those deer. That is, they may be close to dying because they don't have food. Does that make sense? That's sort of the justification behind hunting as far as ecology goes. You want to not minimize the number of organisms, but you want to reach a happy medium where you've got a certain number of organisms that are of a high quality and are able to reproduce to continue that population in the future. Certain traits are going to impact an organism's ability and productivity of reproduction. Those are going to be the things that make up their life history traits. We have 3 different types of organisms. We have type 1 organisms, type 2 organisms, and type 3 organisms. Type 1 organisms are like humans. We produce a very low number of offspring, and we invest a lot of time in them. And then because of that, our life expectancy is extended. We have a much longer life expectancy than most other organisms. Just to show you, how many of you guys are still living at home? Right? Your parents, here 18, 20 years later, are still investing in their offspring. I am not looking forward to my kid. I'm freaking out right now. My kid has to go away to college next semester, and it looks like it's going to cost like $45,000 freaking dollars a year. I know, that's nuts. She's already finished like all her stuff with, like, you guys are done, the gen eds. $45,000. I'm going to be investing that in her for reasons, because my wife says so, I think. And because of that, she'll have a good start to her life, the resources she needs to get going to keep this process moving ahead, keep the species going. Other organisms, type 2 organisms, birds. Birds invest some time in their young too, right? They sit on their eggs, they hatch their eggs, they bring them some food. And as soon as possible, they kick them out of the nest in order to start the next batch. So they end up having not all of the birds survive. I don't know if you guys have ever seen like baby bird that's been kicked out of the nest and died. It's kind of sad. You're like, oh, you weren't ready for life. Typically, birds are going to have that lower life expectancy. And then trees. Trees, they don't care. Trees just don't care. They will drop seeds like crazy. They produce the seeds and then drop them. They produce hundreds of thousands of seeds. Very, very few survive. Those that do survive, the number of individual survivors, is going to decrease over time, but you do get some that survive for a long time. All of these reproductive strategies work. None is better than the other. They're just different. So life history trait, what makes these type 1, type 2, and type 3 organisms different from each other is the age at reproduction, the initial age of reproduction, how often the organism is able to reproduce, and how many offspring are produced per reproductive episode. So again, for your presentations, you're going to need to figure all that out for your organism. For humans, the age of first reproduction is early teens. That's when you're capable of reproducing. Doesn't mean it's a good idea, but that's when you're capable of reproducing. How often you can reproduce. A human female can reproduce roughly once a year. How many offspring do they produce? 1 each time, except in rare circumstances. Compare that to cats. Cats are reproductively viable, I think within the first year, maybe a year and a half. Then every 3 to 4 months, they can produce a litter of 10 to 12 kittens. Totally different reproductive strategy than we have. What triggers whether you're going to be a type 1, type 2, or type 3 organism is going to be selective pressure. What are these very selective pressures on your population? And that's going to influence the number and the size of the offspring. Some organisms produce a single large organism. Great white sharks produce, is believed, 1 baby shark per reproductive episode. 6 foot long when it's born. Can you believe that? A 6-foot baby shark. Totally ready to hunt on its own. In order to do that, there were about 10 to 12 pups that were in utero with that great white shark. The one shark that was born cannibalized the other ones in utero to get the energy it needed to survive and grow and take up all the space. Is that all? Yeah. That's what happens. Then, and as far as parental concern goes, the mother great white shark actually has a chemical that triggers in her brain that makes her so she's not hungry after giving birth, because she will 100% eat her offspring. Think about trade-off between number and size. Usually the larger an organism is, the more you've invested in it, the more likely it is to survive. So if you produce a ton of tiny, tiny babies, cool, you've invested less resources, and you've produced more of them, but each one is individually less likely to survive. Chances of one of them surviving to adulthood are roughly the same as the single large one of surviving to adulthood. So, animals and plants whose young are more likely to die often produce a whole bunch of babies. Plants typically are going to produce way, way more seeds than the environment will support. For us, a lot of mammals, by the extra investment, we increase our offspring's chances of success. It becomes tricky, though, when you're actively competing with offspring. Giving this extra care, giving these extra resources will allow your offspring to compete in a high population density. I know I'm looking at my offspring thinking they're going to have to compete with you guys. So what am I going to do to give them the best possible push-off, give them the best possible, chance of survival? Well, I'm equipping them with, obviously, I spend more time teaching them than I teach you guys, because honestly, I spent yesterday talking to my son about, he's in 9th grade. We spent a while talking about, what were we talking about? It was amphipathic molecules and I can't remember the term. I always forget this term. It's the same term I forgot with you guys when I was teaching you about the liver and bile salts. They break fats up into smaller globules. Shoot, guys, come on, give me the word. Yes, thank you, emulsifying agents. I sat there yesterday for a half hour, 45 minutes talking to them about emulsifying agents and amphipathic molecules, which I don't know how that's going to help them later, but there we go. That's my contribution. It should help for later competition. How about this? You guys see it all the time. You got you'll watch rich kids, and you think, man, they've got it easy. They're going to probably be highly reproductively successful because they've got the resources. Some controls on this are density independent. They control the size of a population. The density, populations that have density-independent changes are where the birth rate or death rate doesn't change with the population density. Density-independent checks on a population's growth are going to be things like forest fires. Doesn't matter how many organisms are present, a forest fire is going to mess you up. Tornadoes, natural disasters. They do not matter. They will damage a population, whether it's large or small. That's compared to density-dependent changes in a population structure. In this case, the birth rate or death rate does change with population density. The more organisms that are present, the higher the death rate. Competition increases. Think about that with just resources present. The more organisms that are there, the more resources they're taking in. Would a virus be density dependent or density independent? Does a virus's spread through a population depend on the size of the population or the density of that population? Yeah? How about this? Think about back to zombie apocalypses. Where do you see zombie apocalypses happening more often? In the city or out in the country? City. Why? Because it's easier to spread from one person to another. A zombie apocalypse would be a density-dependent population event. A lot of density-dependent regulations going to be involved with the competition for resources. Toxic waste product production, that is, if you have a whole bunch of organisms, let's say you guys produce toxic waste products. You excrete things during the day. The more people that are there, the more excrement builds up. Does that make sense? Predation. As far as predation goes, the higher the population of predators, the more the prey population is controlled, the lower the prey population. Territoriality. So depending on what territory size a predator takes on or a group takes on, they're able to regulate each other. And disease, as we talked about with the zombie apocalypse, blah, blah, blah. The zombie hordes coming in. So, questions on density-dependent population growth. Checks on population growth from density. If you don't have enough resources, you die. The more organisms that are present, the more resources they need. If those resources aren't present, the population decreases. If you build up too many toxic resources in the environment around you, because nobody likes to live in their own stench, you're going to decrease the population size. If you have a predator that's actively attacking you or trying to hunt you down, the population size will decrease. If you cannot maintain your territory from other interlopers who are trying to get in, your density will decrease because you got to leave. And of course, disease. If you have a disease, that disease will spread more quickly among a large, highly dense population than among a smaller, less dense population. Over time, populations change. And those dynamics among different communities, among different groups in the population will change. Sometimes you'll have, like I said earlier, we have some trees that will put out poison to kill other trees around them. And then as that tree dies, it encourages more growth around it from new species. Questions or concerns?